We are going to look at lesson 3.1 on page 283 of your textbook. This lesson is titled 88 miles per hour and is referencing slope as a rate of change. The beginning paragraph gives us an example of a common rate of change, speed. In fact, they use the rate of change from Back to the Future. 88 miles per hour is an example of a rate of change. Under the section where it says 3.1 class, the author goes into some more detail about what it means to be a rate. A rate is a ratio that compares two quantities. By rate of change, we mean a rate that compares the change in one quantity to the change in another. A speed like 88 miles per hour qualifies because we can write it as 88 miles over 1 hour. This quite literally compares a change in distance, the 88 miles, to a change in time, 1 hour. That's exactly why we measure speed in miles per hour. The word equivalent is an important word in math, and it's one that we use often. For our purposes, we'll say that two quantities are equivalent if they have the same value or are interchangeable even if they look different. Number 1 at the bottom of the page says if you make $100 a day for doing a certain job, how much money would you make in a 5-day work week? Well, we're going to take 5 days times the $100 per day, and that gives us a total of $500 in 5 days. Question number 2 wants us to address then if $100 per day and $500 in 5 days are equivalent rates. Our answer to this is yes, absolutely. They're equivalent because $100 per day is the same amount of earning if you earned $500 in 5 days. So we will say yes, these are equivalent rates. Turning the page to page 284, it says, question 2 demonstrates a useful fact about rates of change. They can be scaled up or scaled down to fit a given situation. Scaling up means using larger numbers, scaling down means using smaller numbers. These processes are done by either multiplying both the numerator and denominator by the same number, or dividing both the numerator and denominator by the same number. Number 3 asks us to write a fraction equivalent to 60 miles in 4 hours that has a 2 in the bottom. Well, how do we turn a 4 into a 2? It's getting smaller, so we need to divide. If I divide 4 by 2, that's going to give me a 2 on the bottom. Remember that with fractions, whatever I do on the bottom, I have to do on the top. 60 divided by 2 is 30, so my new numerator is 30 miles. 4 divided by 2 is 2, so my equivalent rate is 30 miles in 2 hours. Number 4 wants us to get even smaller. They want us to take 60 miles over 4 hours and rewrite it so there is a 1 in the denominator. This is known as a unit rate because it's a 1 in the bottom. It's getting smaller, so again I have to divide top and bottom by the same number. What do I have to divide 4 by to turn it into a 1? I have to divide it by 4. I divide top and bottom by 4. My new numerator then is 60 divided by 4. You can use a calculator to calculate that. It is 15 miles in 1 hour. 5 presents an interesting problem. 5 wants us to take $320 in 4 days and change it so that it has a 10 in the denominator. Thankfully, they give us a hint. They ask us to scale down and then up first. So let's scale down all the way to the unit rate. Let's divide top and bottom by 4. 320 divided by 4 is $80. 4 divided by 4 is 1 day. So now I've converted it into a unit rate, which is $80 per day. I'm still trying to get to a 10 on the bottom, so I'm going to scale up now, which means I have to multiply top and bottom by the same thing. I have to multiply 1 by a 10 to make it a 10. And whatever I do on the bottom, I also do on the top. 80 times 10 is 800. One times 10 is 10 days. So we will make $800 in 10 days if we continue to work at that same rate. Moving on to number 7. It's towards the bottom of page 284. We're looking at a different example now. It says most experienced runners get to a point where they can comfortably jog long distances at a consistent pace. This pace, of course, is just another way of saying rate of change, because speed is the rate at which distance changes compared to time. One particular runner jogs 1 lap around a 400-meter track in 2 minutes. We're going to assume that they maintain this pace. So number 7 just says for every 2 minutes, they jog 400 meters. That's given in the problem. They want us to use this information to complete the table. They've filled in the first part. After 2 minutes, they've run 400 meters. After 4 minutes, we're going to add another 400 to that. 400 plus 400 is 800. They want us to continue going up by 2 minutes each. So I'm going to go 6, 8, 10, and 12. And every 2 minutes, they add another 400 on. So I'm going to take 800 plus 400. So after 6 minutes, they have run 1,200 meters. Add another 400 now on. After 8 minutes, they have run 1,600 meters. Add 400 again to get 2,000 meters. Add 400 one more time to get 2,400 meters. Now that we've filled in a chart, we can answer some questions about it. Turning to page 285, top of the page, it says, notice that the rate at which the runner's distance changes is constant. When the rate of change is constant, this quantity illustrates what type of growth? We dealt with this in Unit 1. The 2 types of growth we dealt with in Unit 1 were either linear, which formed a straight line, or exponential, which formed a curve. A straight line means there's a constant rate of change. So since this one is always changing by 200 meters or 400 meters each time, this is considered linear growth. It's constant. Number 10 asks us to write the runner's rate as a fraction using meters in the numerator. Well, we know that my runner goes 400 meters in 2 minutes. Number 11 asks us to convert that into a unit rate. Remember that a unit rate means that there's a 1 in the bottom. So I'm going to take what I wrote in number 10, I'm going smaller, so I'm going to divide top and bottom by 2. So my unit rate is that my runner goes 200 meters in 1 minute. These are equivalent rates. They both mean the same thing. Number 11 is written as a unit rate. Number 12 brings back some stuff we learned in the last chapter. They ask me to convert my rate from number 11 to meters per second using dimensional analysis. So I'm going to start with my 200 meters per minute. And I want to make minutes go away and turn it into seconds. Recall from the previous chapter that if minutes is on the bottom, to make it cancel out, I've got to put minutes on top. And I'm going to put seconds on the bottom. I know that there are 60 seconds in 1 minute. Now, if you look at what happens, my minutes cancel out and I'm left with seconds. Now I have to do the arithmetic. 200 times 1 is 200. I just have a 60 on the bottom. Let's go ahead and use our calculators to take 200 divided by 60. They asked me to round to 2 decimal places, so I get 3.33 meters per second. (13) and 14 are very similar. 13 says, how far will they go in 40 minutes? Well, I need to go back to my 200 meters per minute. And multiply that by the 40 minutes given in this problem. You will see again that minutes cancels out, and I'm left with just meters. So go ahead and do the arithmetic. Do 200 times 40. You can use the calculator to do that. And you find that our runner will go 8,000 meters. (14) wants to know how far my runner will go in 40 seconds. So I have to use the number I found in 12. My 3.33 meters per second, and then multiply that by 40 seconds. You'll notice again that seconds will cancel out. I will be left with meters, which just makes me happy. It's where I want to be. So go ahead and do the arithmetic now. Take 3.33 times 40 on your calculator. You should get that our runner goes 133.2 meters. So 15 asks us to bring this all together now. It says, based on the previous 2 questions, can you write a formula for finding the distance when you know the speed and the time? Well, what we did in 13 and 14 is we found that the distance was equal to the speed times the time, times how long they were running for. One more question, turning the page to page 286. Number 16 says, what would this runner's total time be for a 10K race? And they do tell me that 1 kilometer equals 1,000 meters. I will need that. So the first thing I want to do is turn 10 kilometers into meters. I want kilometers to go away, so I'm going to put them on the bottom and meters on top. Using the information in the problem, I know that 1 kilometer is 1,000 meters. So now kilometers goes away, I'm in meters. That's a good start. Now I can use information from the previous page to turn meters into time. I know that my runner goes 200 meters, putting it on the bottom so meters will cancel out, in 1 minute. Now meters cancels out. I'm left with minutes, which will answer my question. That's time. So let's multiply everything on top. 10 times 1,000 times 1 is 10,000. On the bottom I have 1 times 200, which is just 200. Then use your calculator to divide that out. 10,000 divided by 200 is 50. So my runner that I've been dealing with for the last several problems will run a 10-kilometer race in 50 minutes.